Greetings, YouTube. Beautiful Mind here. So this presentation is going to serve as the lecture. This is week 6, day, I think it's day 11 for our Calculus for Business course. So we're going to be continuing. Oh, you know what? I'm so used to doing it with the live homework sessions. Give me just a moment. I gotta actually pull the lecture slides. I'll be right back. try this again. Let me see my time. So 8 minutes. So hour 15, like an hour 20. Okay. All right. So we'll do the best we can for the next like hour and 15 minutes. I'll just have to kind of be aware. Let me see. Hey Siri, set a timer for 1 hour 10 minutes.
Okay. Your timer is set for 1 hour and 10 minutes.
So, so yeah, like I was saying before, this is going to be the lecture. This is week 6, day 11 for calculus for business. And so we're continuing chapter 3 on applications of differentiation. And we're moving into section 3.3, graph sketching, asymptotes. Here, let's hop over here. Maybe it'll be a little bit faster. Asymptotes and rational functions. The objectives here, some objectives. Find limits involving infinity. Determine the asymptotes or asymptotes of a function's graph, and then graph rational functions, okay? So let's explore some of the concepts here. So let's see, we have a rational function is a function that can be described as basically one function over another. Okay, in this case, where P and Q are going to be polynomials, all right? So we have one polynomial over another, where Q is not the zero polynomial, and the domain of F consists of all inputs X for which the denominator is not zero. So basically, the domain here is going to be the domain of each function, provided that the denominator is not zero, okay? So the line X equals A is going to be a vertical asymptote if and only if the following statements are true. So as X approaches A coming from the left, right here, as X approaches, the limit as X approaches A coming from the left of a function is going to be in positive infinity. The limit as X approaches A from the left goes to negative infinity. The limit as X approaches A coming from the right goes to positive infinity. Well, the limit as X approaches A from the right goes to negative infinity, right? So these are like where you have like the dashed lines. As you get closer and closer to this X value, the Y value goes off to either plus or minus infinity. As we approach an X value coming from the left or the right side of that value. Okay. So the graph of a rational function and never crosses a vertical asymptote if the expression that defines the rational function of f is simplified, meaning that it has no common factors other than -1 or 1, then a is an input that makes the denominator 0. The line x equals a is called a vertical asymptote. So if we're simplifying a rational function and you get to a value that makes the denominator 0 and the numerator anything other than 0, that's going to indicate that we have a vertical asymptote, right? Some number divided by 0. Okay, so determine the vertical asymptotes of this function given by this. Okay, so the vertical asymptotes are going to occur where x, so first we need to simplify, and then the x's that make the denominator 0 are going to be vertical asymptotes. Okay, so like you might be tempted to say x equals 0, 1, and -1, but when x is 0, that makes the top and the bottom 0 in this case, so that's actually going to be a hole in the graph and not an asymptote. So if we simplify, we'll get this is gone, and then so that means the vertical asymptotes are going to occur when x is plus or minus 1. That's it. Okay. Since x equals 1 and -1 make the denominator 0, these are going to be a vertical asymptote. So again, they simplify. Notice that the x's are gone, and then plus or minus 1. Now see here, the vertical asymptotes should be what? Plus or minus 4 and 0. Because it's nothing to simplify, right? So then we have these three. Okay. So the line y equals b is a horizontal asymptote if either or both of the following limit statements are true. As x goes to the far left, as x goes to negative infinity, f of x approaches some number, or as x goes to positive infinity, f of x. The limit as x approaches positive infinity of f of x equals some number, right? Okay, let me see how they develop it. So the graph of a rational function may or may not cross the horizontal asymptote. So we can cross, it may or may not cross the horizontal asymptote. The horizontal asymptote occurs when the degree of the numerator is less than or equal to the degree of the denominator. The degree of the polynomial in one variable is the highest power of that variable, right? So if we have one polynomial over another, let me see. We're going to have a horizontal asymptote if the degree of the numerator is less than or equal to the degree of the denominator. So it says determine the horizontal asymptote of the function. So notice the degree of the numerator here is 2. The degree of the denominator is 2. So that means that they're equal. This horizontal asymptote should be the ratio of the leading terms. Now to solve this, what we're going to do, we're going to factor out x squared from every term, right? What we want to do, we want to consider the limit as x goes to infinity, right, of this function. So first we're going to manipulate the function. We're going to consider the limit as x goes to infinity. Now if we factor out x squared, we can transform the function into the following. X squared times is going to be 3 plus, I think, 2 over x minus 4 over x squared divided by x squared times, you're going to have 2 minus 1 over x plus 1 over x squared, right? Notice here our x squareds cancel, okay? And so now if we let the limit, now if we take the limit as x goes to infinity, like for instance, if we look at this term here, let's go like this. If we look at this term here, if you think about, like, if you did 2 over 1, that would be 2. 2 over 2 would be 1. 2 over 4 would be a half, you know, so on and so on. So notice that as this denominator gets bigger and bigger and bigger, this term itself gets closer and closer and closer to 0. So as we let x go off to positive infinity, this term goes to 0, this term goes to 0, this term goes to 0, and this term goes to 0. What does this leave us with? This leaves us with just 3 over 2. Okay. Okay. My dog is making the weirdest sounds. I've never heard her make that sound before. She sounds, anyway. Yeah. Let's see. Okay. Let's see what's happening. So first divide the numerator and the denominator by x squared, right? So we basically factored out the x squared. Find the limit as the absolute value of x gets larger and larger and larger. So notice, okay, in either case, we got this. So therefore the line y equals 3 halves is going to be the horizontal asymptote. Let's try another one. I'm going to let this one be. I'm going to leave that as an exercise. Check my time. Okay. So it says we have this definition. A linear asymptote that is neither vertical nor horizontal is called a slant or oblique asymptote. For any rational function of the form f of x equals p of x over q of x, a slant asymptote occurs when the degree of the numerator is exactly one more than the degree of the denominator. A graph of a graph can cross a slant asymptote, so it can cross the slant asymptote. Find the slant asymptote. Okay, so here notice that the degree of the numerator is exactly one more than the degree of the denominator, right? 2 over 1, right? So here we basically want to do polynomial long division. So we're going to say the top divided by the bottom. So let's do polynomial long division. We have this x minus 1. We want to divide that into, now we have some placeholders. We got x squared. I'm going to add this placeholder of 0x minus 4, okay? So then if we do polynomial long division, x squared divided by x leaves us with x, okay? So I'm going to put my x here. If I multiply back, now I'm going to get x squared minus x. And remember, we subtract, so I got to distribute my negative. And the result there is x, right? Then a negative 4 comes down. Okay? So now if we say the first divided by the first again, x divided by x is 1. So we're going to say plus 1. We multiply, we're going to get x minus 1. And again, we got to distribute a negative, so this becomes negative, this becomes positive. Okay. Negative 4 plus 1 is negative 3. All right, so the equation of our slant asymptote is going to be y equals x plus 1. That's going to be the equation of our slant asymptote. Okay. So again, whenever the degree of the numerator is exactly one more than the degree of the denominator, then we have a slant asymptote, and we find it by doing polynomial long division. Let's see it here. Okay. I'm going to leave this one as an exercise. Oh, is that it? No, that's not it. Okay. So now we want to take these notions of finding asymptotes as far as the vertical, the horizontal, and the slant, and incorporate it into our curve sketching, right? Graph sketching. So it says asymptotes of exponential and log functions. An exponential function of the form a times e to the bx, where b is positive, has a horizontal asymptote y equals 0, which is the x-axis, as x goes off to negative infinity. Exponential function of this form where b is negative, so where the exponent is negative, has a horizontal asymptote that goes off, which is the x-axis, y equals 0, as x goes to positive infinity. Right? Remember for the first one, the general graph of an exponential starts close and takes off like that, right? If we make the exponent negative, it's going to be like exponential decay, right? That's the second one. Log function, the general form of a log, comes up the y-axis and it goes off to the right like that. So it says a log function of the form natural log of x minus a has a vertical asymptote x equals a. As x approaches a coming from the right, right? So, that's where this is coming. This is coming in. Instead of x minus a, if it takes on the form a minus x, it has a vertical asymptote as x approaches a from the left. Okay. Okay. So let's give it a go. Let's see. Find the horizontal asymptote. So as x goes off to positive infinity. Let me think about it. Okay. So I'm just going to focus on this term here. I just want to focus on this guy here for right now. So if we focus on this 25 e to the negative 0.04x, I want to consider that as x goes off to positive infinity. What happens to this term? So as x goes to positive infinity, the exponent, let me see. We're going to get 1 over, so that's going to go to 0. Looks like it's 200, right? So if this has a negative exponent, this is like a fraction, so it's 1 over e. Then if we're going off to positive infinity, right? So here, let me write out this thought process. So I want to consider this, like I'm considering the limit as x goes to positive infinity of this guy here. This is going to be the same as the limit as x goes to infinity of, you got 25 over e to the 0.04x, right? Because you have the negative exponent. So as x goes off to infinity, this denominator, this guy here, let me do, I guess, this color. This guy goes off to infinity. All right. So again, some number over infinity, which means, okay, so let me go back to the original. If we consider the limit as x goes off to infinity, you got 1 plus 25 e to the negative 0.04x under 200. This guy essentially goes to 0 because of that negative exponent. This goes to 0. So it looks like it should be the as x goes off to the far right, we should get y equals 200. Should be our horizontal asymptote. Okay, let's see how do we do. Okay, let's see what how the book did it. So as x goes off to positive infinity, again, this term goes to 0, right? So therefore, the limit as x goes off to positive infinity of the original expression is going to be the same as 200 over 1 plus 0, which is basically 200. So the line y equals 200 is going to be the horizontal asymptote of the function. As x goes to negative infinity, double negative will be positive. It would go to 0, right? Yeah, some kept saying look at negative infinity because you're going to have basically a fixed number over infinity. So then that's 0. So that means to the right, it goes up to 200, and going off to the left, it goes to 0. So going, yeah. So we have two. We have two. So we got one of them. I think we did miss one, right? So this is going to be the graph of this function. To the right, we have our horizontal asymptote as we go off to the right, and we have a horizontal asymptote as we go off to the left, right? So if you look at this graph, that kind of explains why we're getting a result like that. Okay. All right. So some suggestions for curve sketching. So a strategy for sketching graphs. First, you want to consider any intercepts or any x and y intercepts. I usually do the y intercept first. Oftentimes, to me, that was a little bit easier than the x. Sometimes the x can be a pain. Okay. Then you might want to consider any asymptotes. So you want to find any vertical, horizontal, or slant asymptotes. You want to look at f prime and f double prime. Then find any critical values. It should be some more. You want to determine whether the function is increasing or decreasing and find any relative extrema. And then we also want to look at inflection points, right? So how many is that? Is that 6? A, B, C, D, A, B, C, D, E, F. Mm-hmm. So let's give it a go. We're going to take some, oh, wait, it keeps going. Then we have concavity because that gave us points of inflection. Then determine if it's concave up or concave down. And then you want to plot, choose a few additional points between and beyond all of these points that we found, and then do a nice sketch. So this is going to take a little while. So let me see. Let me check my time. I guess I didn't have to hop there. I think we're okay. So my time, we have about 50 minutes. Okay, so we're gonna give it a go because I know we did one in the homework, and it took up the whole class time. Like, so this is asynchronous, so you have time. You just gotta go for it. You know what I mean? I know it's a lot, but now we asked to sketch the graph of this. So what I'm gonna do, I'm gonna give myself some space. Okay, let's go paper. I usually like to write on graph paper. And I'm going to get a copy of this. So I don't need this. And I want to get a copy of this guy. Okay. Drop it right there. Okay. And like this, and like that. And we're going to go view, and I want to do seamless. And let me just go ahead and add another page. Okay. All right. So we're asked to sketch the graph of this function. So first place to start, let's look at any intercepts. Okay, I think we stopped at 6, but there were like a couple more, 6, 7, 8. I think there were a total of 8. But anyway, and I usually like to start off with the y-intercept. All right. So for the y-intercept, we set x equal to 0 and solve. So if we set x equal to 0, we get a y-intercept of what is that? 8 divided by -4 is -2. So the y-intercept we get is 0, -2. right? I usually like to start there because it's just that quick, right? Let's consider any x-intercepts, okay? So for the x-intercept, we set y equal to 0 and solve. Set y equal to 0 and solve. So now a fraction is only going to be 0 when the numerator is 0. This numerator is never going to be 0, so no, I'm going to say none for that one. None. Okay. Okay. So now, my thought process, if we can set the numerator equal to 0, we could also set the denominator. And so that's going to lead us into any asymptotes. So I think I'm just going to go, this is just my natural progression. So I'm going to consider any asymptotes. Asymptotes. All right. So first I'm going to set the denominator equal to 0. That's all. Okay. So if we set the denominator to 0 and solve, we get x squared minus 4. So we're going to say x squared minus 4. We set it equal to 0. You can add the 4 and take the square root. X equals plus or minus 2, right? So notice we don't get 0 over 0. So these are candidates for asymptotes. These are going to be our asymptotes, right? Okay. Let's see. There's no slant asymptote because the degree of the numerator is 0. The degree of the denominator. Oh, so let's talk about horizontal, right? So horizontal asymptote, the degree of the numerator is 0. The degree of the denominator is 2. So what we want to do for horizontal, we're going to take the limit as x goes off to plus or minus infinity, right? I'm just going to do the limit. Let's say horizontal asymptote. Okay. I'm going to take the limit, and let's do it like this. I'm going to consider the limit as x goes off to positive infinity. We got this 8. It's x squared minus 4 under 8, right? So first we want to factor out x squared from the top and the bottom. So this is going to be the same as the limit as x goes to infinity. We're going to have x squared times 8 over x squared over x squared times 1 minus 4 over x squared, okay? Notice these guys cancel. Now if we take the limit as x goes to infinity, this term goes to 0, this goes to 0, right? So we're going to be left with 0 over 1, which is equal to 0, all right? So then the horizontal asymptote is going to be y equals 0, okay? Yeah, I'm going to let that be for now, okay? So then I think the next suggestion was look at the derivatives to find any like max and min and any, you want to look at the first and second derivatives. So we'll say extrema is the third one, extrema. Find any extrema. Okay. So let me get a copy of the original x. So the original f of x equals, we got this x squared minus 4 under 8. Okay. So then the derivative of that is going to be, I'm going to use the Lodi high. So the bottom times the derivative of the top. Okay, so that's going minus the top times the derivative of the bottom is going to be, what, just 2x? So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay. So it looks like we get negative 16x over, I'm going to leave this as x squared minus 4 squared. Okay. So then the candidates for critical values are going to occur where this is either 0 or undefined. So we want to consider x equals 0, this is going to be the undefined at what? Plus or minus 2. Okay. So what I'm going to do, I'm going to plot these on my number line. Let's try that again. Here's my positive x. Here's 0. Here is negative 2. And here's positive 2. Is that slanted? That surely is. That's irking me. Okay. And here's positive 2, right? Now, if we consider f of x, the original function, let me see. When x is 0, I think the corresponding y was, let me write it as an ordered pair. So we had 0 comma negative 2. I think this was an asymptote here. This was an asymptote. Okay. Let's look at the first derivative. Now, if we plug 0 into the first derivative, I think it makes the original function 0. If we plug in these are undefined. Okay. So then we want to choose test points between and beyond these values on the left and the right. Now, if those are going to be asymptotes, well, I guess we still want to determine if the function is increasing, decreasing, or constant or whatever. So on the left, like to the left of negative 2, say when x is negative 3. If we plug negative 3 into the first derivative, this is going to be positive. 9 is going to be positive, so it should be positive, right? So the derivative is going to be positive over here, which means the original function should be increasing. Between negative 2 and 0, I'm going to choose negative 1. If I plug negative 1 into the first derivative, this is positive, so it should still be increasing. To the right of 0, I'm going to choose 1. This is going to be negative. Wait a minute. Wait. I said negative 1, right? 1 minus 4 is, yeah, it's still going to be positive, right? Because of that square. Okay. So if we plug in 1, this is negative. And for the same argument we just did, this is going to be positive. So then there's going to be negative there. And that means the original function should be decreasing. And then to the right of 2, let's choose something like 3. This is going to be negative. This is going to be positive. So the original function, this is going to be negative. The original function is decreasing, right? Okay, so that means according to this, we should have a relative max at 0, comma negative 2 should be a relative max, okay? Let me label it like this. We're going to say max. Okay. We need to also look at the second derivative. That's going to tell us about, like, I'm just say concavity. So I'm going to say number 4 is concavity. Okay. So we want to look at the second derivative. Let's add a page. Let's see my time. Okay. Man, I do not be having the energy, like, all right. So like just back-to-back lectures. Second derivative. So if f prime, on bottom we had this x squared minus 4 squared. On top we had negative 16x. So now I want to consider f double prime. Okay. So I'm just going to do my Lodi high again. So the bottom, which is this guy, times the derivative of the top, it's just going to be negative 16 minus the top times the derivative of the bottom. Oh, derivative of the bottom, we got to do 2 times x squared minus 4 times 2x. So we got to get another 2x in there. Okay. And I'm gonna just get this all on one line. Yeah, let's undo. Okay. Let's get the whole thing to be consistent. Okay, let me, and then over the bottom squared. So now it's going to become x squared minus 4 to the power of 4. Okay, let's check real quick. The bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be this 2, all of that times the derivative of the inside. Okay, all over the bottom squared. Okay. Now notice they both have the following: x squared minus 4, 16, it's no extra x there, so just 16 times x squared minus 4. So they both have, let me see, this, 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 and this. Okay. Okay. So let's factor out that 16 x squared minus 4. So this is going to be equal to, we're going to have 16 times x squared minus 4. Now what's left? In the first term, it looks like, I guess it might be a little bit more simple to factor out a negative 16, because they both do have that negative 16. Let me do like this. Okay. So if we factor out the negative 16, now what's left, we got what? X squared minus 4. Okay. 2x times x is 2x squared. So then it's going to be 4x squared. So we're going to say minus 4. Oh, that's it. Minus 4x squared. All right, because that's gone already. Okay. Over x squared minus 4x to the power of 4. Okay. So hopefully we're keeping track. We got this x squared minus 4 changes this to a 3. And we can like simplify a little bit further. So our claim is that f double prime of x. Okay, we can do negative 3x squared minus 4 over x squared minus 4 to the third power. Okay, I'm going to go with it. So then so when the second derivative is either 0 or undefined, those points are candidates for points of inflection. Right, the point of inflections, if there are any, are going to occur when the second derivative is either 0 or undefined. Okay. So if we set the numerator to 0 and solve, we got this negative 3x squared minus 4, right? Let's see. I think we're going to get a non-real result, right? If we add 4 and divide by negative 3, x squared equals negative 4 by 3, right? You get an imaginary result. So we don't get a result there for the numerator. Let's check the denominator. So basically, we would set the denominator to 0. Let me see. I guess that would make it undefined. No. Okay, let's set the denominator to 0 and solve. So we have this x squared minus 4 cubed. equal to 0. Cube root on both sides. X squared minus 4 equals 0. Add x squared equals 4. And these are points of inflection where it goes from concave up to concave down. Okay. Okay. Plus or minus 2, right? So these are the vertical asymptotes. But what should happen, what may happen is the graph is going to go from, it might go from concave up to concave down. Right? Even though it's not going to be a specific point of inflection. So if we go back to this thing, I want a copy of this. We're almost there. I think we're past the hardest part of this example. Copy. And let me add another page. Paste. Okay. So now if we consider the second derivative, remember these were asymptotes. All right. I think we just had plus or minus 2. So now, to the left of negative 2, let's see what happens if we plug negative 3 into the second derivative. So if we plug negative 3 in, this is going to be negative. This is negative 3 squared is 9. This is positive, right? So it's going to be negative. It should be concave down. So to the left of negative 2, I got that the second derivative was negative, so it should be concave down. Let me see if I plug 0 into the second derivative. The top is negative. The bottom is negative, double negative is positive, right? So I got that it was positive. The second derivative was positive, so it should be concave up. Was that a max? Going from increasing, wait a minute. It's going from increasing, maybe, what are we missing? It should have been, maybe we didn't do something right. Let me go back. Okay. If we plug in negative 3, right? This is positive. The numerator is negative. This is going to be positive. So it should be concave down there. Okay. If that's a max, I would anticipate that to be, that should have been concave down as well. Let me check it again. So if we plug in 0, what's left is we got a negative here. Yeah. And this thing is negative. So double negative is positive. Maybe my second derivative isn't right. Let me look at it. Let me go back. Okay, so there's our first derivative, right? So the bottom times the derivative of the top minus the top times the derivative of the bottom, okay, over the bottom squared. Okay, that looks good. So now we factored out an x squared minus 4 and a negative 16 from the two terms on top. All right, that left us with the x squared minus 4 minus 4x squared. Okay, that should be a negative 3x squared minus 4. I feel like something's a little off. Let me think about it. It should have been concave down. Unless maybe, let me go back to the first derivative. So like if we choose negative 1. Okay. Now if we choose negative 1, this is positive. This is positive. It's positive, yeah. Should have been negative. Oh, let me see. I feel like we're missing something. I feel like those two should be flipped around. Let me think about it. Let me see. From here, the numerator set it to 0. We add, divide, negative 4/3 is never going to be because we get plus or minus. We get an imaginary result there, right? And then those were the asymptotes. Cube root is still 0. Add, take the square root, you get plus or minus 2. I feel like that should be concave down. I feel like this should be negative. Let me look at the second derivative again. So like if we plug in 0, that's gone, that's negative. That's negative. I'm getting a positive result. Let me check the right side of 2. If I plug in 3, right? If we plug 3 into the second derivative, the top is going to be negative. That's going to be what, positive? So it should be negative over there. But you know that the asymptotes are not points of inflection, but it does go from concave. The concavity changes there. What happens when we plug 0 in? Yeah, we get a negative result. Okay, so I'm a little bit stuck here because it's not, I was anticipating these to be kind of reversed, so I feel like I'm missing a negative somewhere, like a sign. Because like if 0 is a max, it should have been concave down. Like I think if all of these were reversed, unless I'm missing some critical value in between -2 and 2. Let me see my time. Well, we got a little bit of time. Let me see. If we add and then divide, you don't get results there. This one, add square root plus or minus. Okay. So the only thing I'm going to just kind of mark, I'm going to asterisk this for right now for the second derivative. And so it looks like we got asymptotes. We got x and y intercepts and put it all together. I'm going to actually just glance at the graph. I'm going to kind of let that be for right now and see if we can find out what are we missing. I feel like there's something that we're missing. Okay. We're going to come back to it. So let's go view, single page. Okay, so let's see how the book did it. Okay. Sketch the graph. Okay, I think we got this intercept for the y-intercept. So again, we said there are no x-intercepts. We got a y-intercept of 0, -2. Okay. Asymptotes vertical, we got plus or minus 2. We said y equals 0 is a horizontal. Did we say that? I think we did, yeah. So these two are fine. So there aren't any slants. Now, the second derivative right here. We got the x squared minus 4. Are we missing? Yeah, they still get plus or minus 2. Let me check my second derivative compared to theirs. Let's see, they had a 16. It looks like I'm missing my 16. That's one thing. Let's see. So that's a negative. Okay, I think I see it now. I think we are missing that -16. So then x squared minus 4x squared is a -3x squared minus 4. We just forgot to bring down this. I was like, yeah, I knew it was something missing. But I was like, whew, I was losing my mind right here. There's -16. Let me change the color. Let me make it pop. So what we were missing earlier was this -16 there, right? I think everything else was fine. So with that being the case, now let's go back and do our analysis again. That's what I was looking for. I was like, we're missing a negative somewhere. I was like, if those were, because when I was looking at this, I was like, okay, I was confident in my first derivative, right, for that to be a max. But in order for that to be a max, the second, this, all of the, basically all of these results had to be flipped. And so I was like, okay, for these to be flipped, well, maybe not all of them, but definitely this one in the middle needed to be flipped. I was like, okay, that was an indicator. I was like, we're missing a negative or something somewhere. So I think we found the missing negative. Now let's go back and evaluate. Let's redo, and I'm gonna do it in purple since we redid the second derivative. I think we found what we were missing. Okay, so -3. If we plug in -3 here, this is going to be positive. This is going to be negative. Double negative is positive. So the top here is going to be positive. This is going to be positive. And so I think we get a positive result here, which means we're anticipating it to be concave up. And I think that's what we want. Okay. So now let's do when x is 0. Right? If we plug in x equals 0, you get -4 times -16 is positive, so the top is positive. I'll just put a plus here. If you plug in 0, the bottom is negative, so ultimately the final result is going to be negative there, which is exactly, yeah, I was like, man, it was driving me nuts. I was like, where is it? I couldn't find it until I looked. I was like, oh, I found it. Okay. And then we're anticipating the far right to be positive. So let's plug in 3. Okay. If we plug in 3, let's see, this altogether is going to be negative, double negative. So the top is going to be positive, right? So this is going to be positive. This is going to be positive, so the final result is positive, okay? So then this is positive. So it should be concave up. Okay, there we go. Man, so I don't think we have any distinct points of inflection. Oh. We don't have a point of inflection, but it does go from concave up to concave down around the asymptotes, right? Okay, now we're cooking. So now let's bring all this together. So if we go back to the beginning, because we have more than enough information, we got a y-intercept of 0, -2. Let me make a table. I'm gonna make a running table, right? So I got my x versus my y. I guess I'll do it like this. When x is 0, y is -2. Okay. Let's see. When x was plus or minus 2, so say we have like -2 here and +2 here, these were vertical asymptotes on our graph, okay? I'm just gonna cut my table and bring it with me. Okay, so we've accounted for the asymptotes. We said a horizontal asymptote, y equals 0, okay? Okay, we said we had a max, so let me note that this was a max. Just need a little bit of space. Okay, we said that this was a max. Let's cut, okay. All right, I think we have, let's kind of put all this together. Let's see, let's paste, okay. So then we just want to choose a few points between and beyond these points that we found. So we can do something like when x is -3, when x is -1, 1, and 3, right? Into the original. Okay. So when x is -3 into the original. 9 minus 4 is 5, so we get 8 over 5. Okay. When x is -1. -1. 1 minus 4 is what, -3? So -8 over 3. Okay. Now we didn't do a test for symmetry. There are more tests that we can do, but I think this is more than enough for right now. When x is 1, think we get the same result. So it should be negative 8 over 3. And I'm just going to say that 3 should be 8 over 5. Okay. So now if we were to plot this, let me see, my x's, negative 3 to 3. My y's, 8 over 5 is what, less than 2? The lowest one is almost negative 3. So if we go maybe 4 on the y-axis. So if we go 5 in all directions, I think that'll cover it. So like if we did 1, 2, 3, 4, 5. Hopefully that should be enough space. I'm going to copy this, paste. Okay. Let me undo. I'm going to add a page. I'm just going to do a whole other page. Okay. Okay. All right. So then this direction is our positive x. Let's try that again. This is our positive y. Okay. Positive x this way, positive y this way. We count it by 1. Here's the origin. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So now, let me move this down. And I'll plot these in blue. So now we said we had a local max at 0, negative 2. So I'm going to plot this point here. We have an asymptote, 2 plus or minus 2 are vertical asymptotes. So I'm going to do it like this. I'm going to go style. Let's see. Should be some options. Where are my options? There they are. We can do it like this, maybe like this, and like this. A bit bigger. This one. Okay, let's copy this. Paste. Okay. So we have a vertical asymptotes at plus or minus 2. We got our max. And then let's plot these few additional points. So negative 3, positive 8 over 5. Oh, we had a horizontal asymptote. I think we said y equals 0, right? Okay. All right. Now, the way I kind of used to do this in the past, I mean, so for instance, like negative 3, when we let x be negative 3, we got a positive 8 over 5. So what is that, a 1 3/5? 3/5, a little bit past halfway. Let's do it like this. Paper. Like this. Okay. 1 3/5. So about there. All right. And if we copy, that same point was, we had 3, and then we're going to have another one about like here. Okay. When x was negative 1, we got a negative 8/3, negative 1. So that's what, 2 1/3, negative 2 1/3 is about here. Paste. right about here. Okay. All right. So now, when we go to sketch the curve, starting on the far left, we should start kind of like close to the asymptote, pass through that point, and finish close to the asymptote. Start close to the asymptote, pass through these points, and finish close to the asymptote. Okay. Here, the far right, start close to the asymptote, pass through this point, finish close. Okay. Should be a graph like this. Okay. So, let me see my time. Okay. I was gonna put it in a computer, but I'm just gonna go with that. And I think everything is satisfied. We said the second derivative, so first it should be concave up, then concave down, then concave up. We got our local max, we got our vertical asymptotes, horizontal asymptotes, and a few additional points, right? So yeah, and I knew that on that second derivative something was off. I was like, but we found it. I noticed increasing, increasing. Yep, it's increasing, increasing, then decreasing and decreasing. That feels good. Okay, so let's go view. I know there's a bit of a journey. We did get a little stuck there, but we got on the other side. Okay, I think we got this y-intercept, no x-intercept. We got our vertical asymptotes. There was no slant. We looked at the first and second derivatives. I think we found the missing 16 that we were missing. Okay, we found it. Critical values. The only one was 0. Okay. We determined, let's see. So this is telling us whether the function is increasing or decreasing. So we didn't, I don't think we had any points of inflection. But we did have concavity. Okay. And I think we got that as well. And this is the graph that we got. Okay, let me see the time. I'm like, that was all of my energy. It's like 12 minutes. Let me try. Let me see. Sketch the graph of this one. E to the. I'm tempted to try it. Okay, let's explore. I don't know how well I'm gonna do because I'm like totally spent. But let's do some exploring, right? So first, and actually, let's give ourselves some paper, some space. I know I have about like 10 more minutes on the clock. We got e to the negative x squared. Okay. This is what? Example 6. Y equals, is it y or f of x? E to the negative x squared. Okay. Okay, so let's repeat our procedure. Last time, the first thing we did, we considered any intercepts. Intercepts. Okay. I usually like to start with a y-intercept because to me that one's often easier. What we're going to do there is set x equal to 0 and solve. And I think we get what, 1? Y-intercept 0, 1. Okay. Then we want to consider, are there any x-intercepts? So if we set this function to 0, I don't think it crosses, right? Because, let me see. So if we set y equal to 0 and solve, we'll get e to the negative x squared equals 0. If we took the natural log on both sides, natural log of 0 is undefined, right? So this won't be 0. So I'm going to say none. None here. Okay. We got this y-intercept. We got no x-intercepts. So then we want to consider any asymptotes or asymptotes. Okay. So the vertical asymptote would occur where the denominator would be 0. Because even though we have 1 over e to the x squared, it won't ever be 0. So there's no vertical asymptote. Let's just see if there's a horizontal. Now, normally the horizontal goes off to the left. I'm going to see what happens as x goes off to positive infinity. So I want to consider the horizontal. Okay. I want to consider the horizontal. I'm going to consider as the limit as x goes off to positive infinity. E to the negative x squared. So this is going to be the same as the limit as x goes off to positive infinity. Paper. This is going to be 1 over e to the x squared. So then this denominator, if we let x go off to positive infinity, this denominator is going to go to infinity, right? 1 over infinity is essentially 0. Oh, let's go view seamless. And let's add a page. Okay. So then this is essentially 0, right? So our claim is that the x-axis, y equals 0. So horizontal, looks like we have a horizontal going off to the right, y equals 0. As x goes to positive infinity. Okay. Now let's look at the derivative. Okay. So before I write extreme and all that, I just want to, let me see, the original, we have this f of x e to the negative x squared. So let's look at the first derivative, f prime. The derivative of e is itself times the derivative of the exponent, which is going to be times negative 2x, right? And then f double prime. So I'm going to do product rule. So the first times the derivative of the second, which is just going to be times negative 2, plus the second, which is this, times the derivative of the first. So basically we got to redo that. It's going to be e to the negative x squared times a negative 2x, okay? Let's see, we can at least, it seems like we got a negative 2 e to the, we could factor out some things here. Okay. This should be the same as, looks like we can factor out a negative 2, and actually my colors helped me last time. They both have the negative 2, they both have this guy, and let's see, this one, and this one. Style. Okay, so we're factoring out a negative 2 e to the negative x squared from both terms. This is going to leave us with what? 1 minus 2x squared e to the negative x squared, okay? Okay, I think this is okay. So now, when will the first derivative be 0? Okay, it's going to be 0 from here. That's going to be the origin, right? Will this ever be undefined if this is 1 over? Will this ever be 0? No. So the only candidate for an extrema, so now let's move into our extrema, which is what, the third category? Extrema. Okay, let me see my time. Got like 5 minutes. So if we look at the first derivative, we want to set f prime of x equal to 0. So then that's just going to be basically the negative 2x is going to be equal to 0 because the first one's not going to be 0. So we get the origin. So this is our candidate, x equals 0. Or actually, not the origin, but when x is 0 is our candidate. If we plug x equals 0 in the original, I think we get 1, right? So a candidate for an extrema is going to be the ordered pair 0, 1. Okay. So we go on number line. Here's positive x. We said when x is 0, okay? Let's go like this. The page is here, Add a page. Okay. So now if we look at the original function, I think the corresponding y is a 1 there. If we look at the first derivative here, when we plug in 0 into the first derivative, I think it spits out 0. So to the left of 0, like say -1, if we plug -1 into the first derivative, what happens? This is going to be positive, positive. So it looks like the first derivative is positive there, which means the original function should be increasing. Okay. So on the right side of 1, sorry, the right side is 0. Let's move this down. Okay. On the right side of 0, say when x is 1, what happens when we plug it into the first derivative? When x is 1, this is positive, this is negative, so the original should be negative. I mean, the first derivative is negative, so the original should be decreasing. Okay. So then the second derivative, if we look at it, when it's either going to be 0 or undefined, let me see. So will this first term ever be 0? I don't think it's ever going to be 0, because even if you plug in 0, you get like -2, right? So we can't get this to 0. Can we get this term to 0? Yeah, we can get this term to 0 because it is x squared. So it looks like 0 is still our candidate. What should, that would be a candidate for a point of inflection. Let me see. If we plug in 0, this is like 1, 0 over 1, so that's 0. Okay. So let's see, what is the second derivative? We would anticipate the second derivative to be negative if we want this to be a relative, what, max? So this is like a relative max. So if we look at the second derivative, f double prime, it's kind of behaving like a point of inflection. It shouldn't be popping up. If we set this to 0, right? Again, this won't go to 0. If we set the second part to 0 and solve, okay. Here, let me write it out instead of trying to do it in my head. So we have this 1 minus 2x squared e to the negative x squared. Okay. I want to set this to 0 and solve. So we can add the thing on both sides. We'll get 2x squared e to the negative x squared equals what, 1? We can divide both sides by 2. We'll get let me think about that. I mean, that's almost a perfect square. Okay. There was a trick here, and I gotta remember what was that trick. I'm missing something here. Let me think about this. Oh, and I think I'm out of time. Like, I got like 1 minute. Okay. So what was the second derivative? Let's see. All right, I'm gonna scan ahead just because I'm out of time. Let me see. So, I think we got that. The derivatives, second derivative. Okay, 4x squared e to the negative x squared minus 2e to the negative x squared. I know I'm missing a 4 at least. Oh, I factored mine out. I wrote it in 2 separate, right? Okay, so I don't think they factored theirs. Right here. So where f prime equals 0, I think we got the x equals 0. Okay. I think we got increasing, decreasing already. Right here, inflection point. So factor 2e to the negative x squared, 2x squared minus 1. I think I left something. I think I didn't factor that properly. Right here. We surely did remove that, and I wrote it again. Okay. Dang, man, I'm like serious about these mistakes today. So we factored out, yeah, I know. Like you were kind of was in my mind. Okay, so we got to go back to our factor. This is where we made our mistake. Negative 2e to the negative x squared, right? So this guy here is gone. Let me strike through it like this. We used this guy already, so that's not supposed to be there anymore. Negative 2x squared. Okay, that's gone. That makes, I was like, man, why is that so bad? I'm gonna leave it so just so we can see the error. 1 minus 2x squared. Let me check it again. That's there. That's there. X, negative 2x. Okay, I think we're okay. So this guy down here. So now it's only going to be when this is 0. Yeah, this helps us out a lot. So this is gone. All of these are gone. I was like, every time I get stuck, I'm like, what am I missing? I'm always missing something. Okay, let's try this again. Delete. So this is what we were setting as 0. This is much easier. So add, we'll get 2x squared equals what? 1. X squared equals what? A half. X equals plus or minus basically root 2 over 2. Okay. I know we're a little bit over time. Okay, so now we set the second derivative to 0. So then our point of inflection, this is like 0.07. Okay. So we can have a negative root 2 over 2 and a positive root 2 over 2. Okay, that's better. Let me see. Hey Siri, what's the square root of 0.5?
The square root of 0.5 is 0.707107.
So this is like 0.07, no, 707,107. 707,107. This is negative 707,107. Okay, positive, okay? So then to the left of that, like if we choose negative 1 and put it into the second derivative right here. And let me just write the proper thing. So this is going to be equal to negative 2e to the negative x squared, 1 minus 2x squared. Okay. So if we plug negative 1 into this, let's see, this term is going to be what? Positive. Then this is going to be negative. Double negative is positive, okay? So it looks like to the left of this, the second derivative is positive, so the original should be concave up. Now if we plug 0 in, let's see what happens. So what is that? That's like 1. So this term is negative. This is positive. So it looks like the original is negative, which makes it concave down. That matches, right? That makes the 0 a max. That matches. And then to the right of root 2 over 2, we can do something like 1. Let me see, positive. So this term is negative. Double negative is positive. Okay. So we get that it's concave up. Okay. All right. Ooh. I'm trying to bring this one on home. Okay. So we got plus or minus root 2, and we got when x is what? 0. We got max. We got, it looks like we got 2 points of inflection. Okay. So now, if we're going to plot this, I would say x, y, okay. We got this negative root 2 over 2. We got 0, and we got positive root 2 over 2. I don't think we had any x-intercept. Okay, we do have a y-intercept. So when x is 0, let me see, I'm going to go like this. So we want to choose a few points between, if this is negative 0.07, so we're going to choose negative 1. We can do negative 1/2. we're gonna do 1/2 and 1, right? So I think this was 1. Let me get a copy of the original right here. We're almost done. I'm gonna let you guys go. Copy, paste, okay. So when x is 0, I think we got 1. I probably should use my calculator at this point. Yeah, let me just use my calculator real quick. I just want to get those raw numbers. And I am going to have to take a break after this. Come on, quick. Right here. I want to reload. Come on. Reload and refresh. Okay. So now, y equals. So if I go to my y equals, my original is e to the power of negative x squared. Okay. So now if I go to I want to calculate. So for instance, when x is 0, we should get 1. Okay, we got that one. So when x is, let's do when x is negative 1. Let me see, if x is negative 1, that's e to the negative 1. So 1 over e. Okay. I'm just going to write out the decimals. So this first one we get approximately 0. I'm going to say 368. 368, all right? Say we did the square root of, we did negative root 2 over 2. Okay. This one was 607. We said that, what's that, a local max? Okay, let's see what we'll do with negative 1/2. Yep, this is adding up. So then we got 0.7, let's say 79. I think it might be symmetric. I'm gonna do a positive 1/2. I think we might have some symmetry going on. Okay. So then we get 0.779. This one should be 0.607, and this one should be 0.368. Okay. So we did as x goes from negative 1 to 1. Okay. So I'm just going to do a quick sketch. Say, let me see. Say 1 is here. So this is 1, this is negative 1. This is the origin. Y looks like it's positive the entire time. So this is just a rough sketch. This is a negative 1/2. This is a half. Y we need to go up to about like 1. So like if this is 1, this would be 0.5. Okay, so we know we had 0, 1 was a point. I think we said we had a horizontal asymptote was the x-axis. Okay, 1/2, we're at 0.7. So here, we're about here. But then we have a repeat of that. Copy, paste. It's like here. 0.7 is about here. It's not drawing a scale. I'm just trying to get out of here. Okay, when it's 1, 0.3 is almost 0.4, so about there. And over here was similar. And then root 2 over 2. So it's like 0.7. There's at 0.6. So about like there. Here. Okay, and now we had a point of inflection, right? Where it went from concave down to concave up. So the negative root 2 over 2. So at these points, it should go from concave down to concave up, about there, about there. Okay, I think we can put it all together. Okay. So we'll have a graph kind of like this. We'll start close to this, close to this asymptote. You can see the point of it is going from concave up to concave down, Concave down to concave up. I like that. All right. I think that hit all the points. Let's see, how do we do? Paper, single, okay. All right. So I think we found our mistake there. Critical values. Points of inflection plus or minus √2 and e to the negative 1/2. Okay, that's fine. Concavity. Yeah, and that's what we got. Okay, and then you see, like, to graph it, you just got the decimals just to get a sense of it. Okay. All right, that was an adventure. Okay, I think I am spent. We're gonna kind of let that be. Ugh. I gotta take a break before we go into the next one. So class starts in like a couple of hours. So, okay. Yeah. So, you know, on that note, we're gonna end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.